Thank you for joining me today. There's a lot of material that I would like to cover in this talk, and so I will begin by jumping straight into an architectural overview of the system. The ADC that I present to you today is a 1 gigasample per second, 11-bit pipelined ADC with 7 1.5-bit stages followed by a 1.5 plus 3-bit backend flash. The core ADC itself isn't really the focus of this talk. Most of the ideas and systems in there have already been described in previous publications, in particular our two papers at ISSCC 2019. These include ideas of fully dynamic power consumption, asynchronous event-driven timing control, an MDAC in the first stage with a passive hold mode, and early quantization for a speed enhancement in the later stages. In this work, we focus on other aspects of the system and introduce some new ideas. In particular, we introduce reference regulation into the overall system design, present the idea of a stochastic scope-on-chip waveform monitoring system, and also innovations on the Ringamp topology, which enhances the speed of the system versus, for example, the design presented in this paper here. Of these three ideas, the first that I'm going to present to you today is the Ringamp topology, because understanding this will also help in the understanding of the next two ideas. Many people are somewhat familiar with, or at least have heard of, what is a Ringamp or ring amplifier. But to briefly answer this question, what is a Ringamp? It's ultimately a multi-stage inverter-based amplifier that's stabilized with a dominant output pole formed by the load capacitance. It uses dynamic large signal transient stabilization mechanisms to enhance performance and efficiency. Benefits of the ring amplifier is high efficiency, high linearity, high speed, wide output swing, fully dynamic switchable or duty cyclable operation, and performance that scales inherently with digital CMOS. Compared to the simple Ringamp topology that I showed on the previous slide, the one shown here, which is the topology that we introduce in this work, is a little bit more complicated. It uses a combination of ideas that people have proposed in the past, and there's no specific technique that's new here. It's really the way that we combine a number of existing techniques into a very elegant structure with many advantages and very few disadvantages. That's the new contribution here. Let's break this structure down piece by piece. To begin with, we can see that this is a fully differential structure with the input inverter stage source coupled on both sides by current limiting tail transistors, which are biased by a common mode feedback network. This common mode feedback network consists of three common mode feedback paths. There's a DC path, which sets the trapped charge bias on this node. There's also an AC path, which allows for a high frequency feedback in cycle-to-cycle operation. And finally, there's a local feedback path around the first stage of the ring amp. In addition to using trapped charge to bias this node B1 that biases the tail transistors of the input stage, we also use trapped charge bias control in the dead zone tuning of the ring amp. The dead zone tuning itself is done with a CMOS resistor, which can be adjusted with these bias DACs in the on state and then switched off as if it was a digital switch in the off state. A switchable CMOS resistor is also used in the first stage of the ring amp. Its function is a little bit different. It's used to boost the overdrive voltage on the transistors of stage 2, which provides an overall speed and efficiency advantage in the ring amp. When you combine these two things together, the CMOS resistor for dead zone biasing and the CMOS resistor for bias enhancement, you end up with a structure that is inherently and elegantly self-resetting. In other words, there's no explicit pull-up or pull-down transistors or power gating transistors required in this scheme. That is to say, in the off state of the ring amp, all of these open like switches, and if the input of the ring amp is roughly at mid-rail, then all of the nodes inside the ring amp will pull to the correct values such that both the output transistors are completely cut off and there is no static or quiescent current through the structure. Finally, we include in this Ringamp topology a so-called slew-done detector, which provides an event trigger signal that indicates when the ring amp's output charging behavior has moved from slewing behavior into settling behavior. This can be implemented, for example, with an analog sensing circuit. However, it's not strictly mandatory to implement slew-done detection with an analog sensor. It's also possible to use, for example, a fixed time delay to generate the slew-done signal. And in fact, we include both options on this chip. I will now describe the fully dynamic reference regulation system introduced in this work. The motivation here is to enable fully dynamic power consumption for the complete system, core and reference, enabling constant figure of merit for any clock rate and enabling reconfigurable multi-standard ADCs. The ADC core is already fully dynamic by design, enabled by asynchronous timing control combined with a ring amplifier that can be rapidly switched on and off. Here we look at the question of dynamic reference regulation. To eliminate static current from our regulator, we must necessarily consider a discrete time regulator loop topology. The simple loop shown here is just a comparator that monitors the reference line and provides charge packet updates as feedback in order to maintain the desired reference level, which is then being drained by the load. The main limitation on accuracy and noise of the regulated output comes from the discrete time dumping of charge packets from the source capacitance into the regulator capacitor, which creates a reference ripple error problem. This is still usually acceptable for ADCs less than 8 bits, but when you go to higher resolution ADCs, the reservoir capacitance that's required to minimize the ripple becomes impractically large. However, it is possible to overcome this limitation, and it's based on a key observation that the reference accuracy and current requirements are decoupled with respect to time. Consider, for example, the Ringamp charging in this 1.5-bit flip-around MDAC structure where the reference charge is being pulled through the Sub-DAC. As the Ringamp waveform charges and slews up, this is when there will be a large initial current pulled out of the reference. In fact, 98% of the total charge pulled from the reference is at this time. During that time, we don't need high accuracy in the reference because we're still coarse charging. After the Ringamp begins settling, it only pulls a small amount of charge from the reference. However, it does require high accuracy. This observation tends to hold true in many applications, not just in residue amplifiers for pipelined and delta sigma, but also in SAR ADCs with redundancy built in, where MSB requirements and LSB requirements in terms of charge pull and accuracy tend to be opposite. The applied solution that this observation suggests is to use 2 copies of VREF, one dirty reference for low impedance, low accuracy, and one clean one for high impedance, high accuracy. By separating this, we relax the requirements significantly on both copies of the reference. Implementation of this idea requires some practical considerations. First of all, we need break before make behavior, such that the dirty reference will never corrupt the charge on the clean reference. Second, we want as fast and clean of a crossover as possible, because when we're making the transition, the amplifier feedback is essentially paused and settling time is lost. We also want the crossover to be as glitch-free as possible so that no errors need to be resettled. The Sub-DAC implementation shown here meets all of these requirements. Our control logic is implemented in a way that ensures this make-before-break operation with a very fast crossover and ensures that no corruption of the clean reference can occur. In addition to the main Sub-DAC switches, a set of dummy switches are also included that cancel clock feed-through and charge injection, leading to transparent operation. All of these Sub-DAC circuits within the pipeline stages are connected to a shared set of regulated reference lines at the system level. The reference regulator itself is clocked at the same rate as the core ADC is clocked, meaning that one update in the regulator occurs per clock cycle of the ADC. In a standard pipelined ADC, we need 3 references. In this system, we need 5 references in order to provide the dirty and clean regulation. For the regulation of the common mode reference, we can get away with just a single dirty reference because the ripple on this line is inherently rejected in a differential structure. About 98% of all the charge delivered from the regulator to the load comes from the dirty references. And this gives them a very unidirectional charge pull characteristic into the load, which also means that as a simplification, the feedback of the regulator can also be made unidirectional. In the case of VREF-P dirty, we always want to source from VDD into the reservoir. And in the case of VREF-N dirty, we always want to dump from the reservoir into VSS. But in the case of the clean references, we don't really know whether we'll need to source or sink. It depends on other variables in the dirty reference lines, and so we have a bidirectional feedback option. The source and sink capacitors must be able to source any amount of charge that the load would need to pull in the worst case scenario, and this sets their sizing requirement. Once these capacitor sizes are determined, the reservoir capacitor sizing can also be determined based on the reference ripple amplitude requirements specified by the accuracy and noise requirements of the system. However, due to practical limitations on the size that we can make the reservoir capacitor, In the dirty reference, which sources most of the charge, the reference ripple is the fundamental limitation on accuracy. However, this is not the case for the clean references where very little charge is pulled by the load and the reference ripple is extremely small. Instead, the fundamental limiter on accuracy is comparator noise, since the comparator noise can still cause incorrect feedback decisions. In our design, we over-design the comparator for low noise operation and then include an option to decimate the comparator in order to save power, only operating the regulator loop once every n cycles. This table gives an idea of the nominal capacitor values that we use in the regulator for the source, sink, and reservoir capacitors. All of these are made tunable for testing purposes, and these test features significantly increase our layout area. With the removal of all those non-essential test features, the layout can be significantly compacted. I will now present another idea that we introduced in this system, that of a scope-on-chip style amplifier settling monitor. This is motivated by the need for ring amps that are robust across PVT. There are two approaches to this. One is robust by good analog design, and this can mean no calibration, but often may require some extra design margin to be built in to pass corners. Still, there's many state-of-the-art designs that have been published using this approach for Ringamp-based ADCs, achieving really fantastic figures of merit. But the speed tends to be a little bit more limited, and this is possibly because of the design margin required. If we really want to push performance, then we can consider the other option, which is robust by background tuning, calibration, or digital assistance. This lets us run the ring amps right at the edge, but it possibly means more complexity in terms of a background control loop. It's also interesting from a research perspective because less has been tried here. This motivation inspires two main goals in this work. The first is a system which is capable of background capture of amplifier settling waveforms in transient operation on chip. And the second is to use that information to optimize ring amp biasing and performance for PVT robustness. In an ideal implementation of a scope on chip, we would place a high-resolution ADC sampling at an extremely high sampling rate at the output of the ring amp and just capture the waveform. However, this isn't practical to implement. There's a number of challenges that we see in the practical implementation. First of all, we have the challenge of a very large residue range, which means that we need a very large input range on this ADC. But here we're actually only interested in this final settling behavior, which has a very small range, in fact. Really, we just want to strip out the DC component to reduce the required range. And this can be done by doing a relative sampling where we compare points on this waveform to the final DC value. This functionality is implemented by having two separate sampling paths in the monitor circuit. One that samples at some point in time along the waveform, and one that always samples at the end. When we take the difference between these two, we subtract out the DC offset at the end and only have the AC waveform. The second key challenge is generating time series capture data. If you look at this settled waveform, it occurs only in a couple hundred picoseconds time window, and to sample this at many points along the waveform with the ADC would require an extremely high sampling rate that's just not practical. The solution is to combine capture data from multiple correlated cycles. If we look at these three cycles, they are not correlated. They have different final output levels and different settling waveforms. But if we encounter at some point in operation something with the same final DC level as this first one, we can effectively consider it to be coming from the same cycle as the original one, because it will have more or less the same deterministic settling waveform. By taking different sampling points along this waveform across multiple correlated cycles and combining them all together, we can then form a final reconstructed waveform that was as if it was from a single cycle. So far, by addressing these two challenges, we've significantly reduced the requirements of the ADC by reducing its input range requirement and also its sampling rate requirement to reasonable levels. However, we can go even further. In fact, it is still possible to get high-resolution capture with a 1-bit stochastic ADC, where we use a comparator's Gaussian noise distribution to quantize. Although our implementation is a little bit different here, the basic idea is to apply a fixed input voltage and measure it many times with a noisy comparator. The output data stream will be a representation of the input voltage as it lies on the input referred noise PDF of the comparator. After some linearization steps, it's possible to linearize this to a digital representation of the input signal with high resolution. If we're willing to accept a little bit of distortion in our measurement, and in the case of transient waveform capture, that's okay, we can eliminate these linearization steps, which are the majority of the computational complexity. Instead, it simply becomes a matter of averaging the output of the comparator. In terms of practical implementation, the 1-bit ADC constitutes the comparator. The data collection and sorting is done in the front of the digital processing blocks, and then finally the averaging is done on individual bins within the sorted data set. At the output of each stage in the pipeline, we place one of these settling monitor circuits onto the negative output node. This single-ended approach has to do with some of the practical issues of our system, but it's certainly possible to do a fully differential implementation as well. That monitor circuit's implementation is actually quite simple. There's some disable switches, the sampling switches, very small sampling capacitors, and then our 1-bit stochastic ADC. Notice that the sampling capacitance that we use is extremely small, and the loading of this circuit on the Ringamp output is negligible. We can get away with this because this noise is actually combined with the noise of the comparator to form the total noise PDF of the stochastic ADC. And in this case, more noise is actually a good thing. The layout of this can be made very compact. At the output of a pipeline stage, the switches can be placed underneath the output lines, and then the capacitors are implemented simply as the routing wires going from the switches into the comparator and controller using this capacitor wire structure shown here. Putting this all together, implementing it, and measuring it in silicon, we see the following measurement results, which provide exciting and direct insight into amplifier settling behavior that we really haven't been able to see before. We can clearly see that when we go into unstable, underdamped, critically damped, or overdamped biasing cases of the Ringamp, the waveform monitor correctly captures and provides insight into that operation inside the chip. With this first goal accomplished, now let's look at how we can use this information to optimize Ringamp biasing and performance. This waveform capture data is rich enough that a number of possible objective functions could be defined from it. I'll show one possibility here. It's based on the observation that only the critically damped case has a large initial amplitude and a final small amplitude. In the case of the underdamped, there's large variation in amplitude both initially and finally, and in the case of overdamped, it's about the same amount of variation in amplitude. If we compare the total power of each signal to just the initial power of each signal, this ratio should give us a good estimator as an objective function. Looking at the output of this objective function across a sweep of Ringamp digital bias tuning code, we see that the objective function correctly peaks out at the best case SNDR value, demonstrating that it's capable of accurately predicting the bias optimum. In this work, we don't close the PVT tracking loop, not only because it's outside the scope of our work, but also because our Ringamp biasing DAC is not designed for monotonicity in this particular chip, and this makes for difficulty in control tuning because of all of these DNL jumps. Background operation of the monitor circuit has a minimal impact on core ADC performance. There's essentially no measurable loss in SNDR or THD, and just SFDR degradation of 3 dB in the worst case. Let's now finish with a performance summary and some conclusions. The ADC is implemented in a 16 nanometer CMOS FinFET technology and occupies 0.095 millimeters squared. At a maximum operating frequency of 1 gigahertz, for 100 megahertz and Nyquist rate input tones, we can see well-controlled spurious content in the digital output spectrum and an ENOB of 9.6 or better. Across input frequency, the ADC shows stable performance up to Nyquist. Across clock frequency, it also shows stable performance, and furthermore shows linear scaling of power consumption and fully dynamic operation, which enables a nearly constant figure of merit from 1 megahertz all the way up to 1 gigahertz. The regulator consumes only 8% of the total system power, with the majority of that power delivered to the load. Looking at a plot of total power versus mode of operation, we can see that the decimation of clean regulators improves efficiency with only a minor sacrifice in SNDR performance of the overall system. For all of the data I've reported here today, we use a decimation factor of 12 in the regulator. To summarize the performance highlights of this system, this is a 1 gigasample per second single channel ADC maintaining better than 9.6 ENOP up to Nyquist with fully dynamic reference regulation enabling constant figure of merit from 1 megasample per second up to 1 gigasample per second. And while this is, I think, a very good figure of merit already, if you look closely at the architecture, you can see that this can be significantly improved further with more aggressive optimization of that architecture. In this talk, I have presented three main ideas. The first is a high-speed Ringamp topology with a particularly elegant mode of operation. The second is a fully dynamic discrete time reference regulation system that can be applied in many cases and can achieve any accuracy or noise requirement for discrete time regulation. The third is a stochastic ADC scope-on-chip-based transient waveform reconstruction system, which is small, simple, high resolution, and capable of background operation. And it leads to other interesting possibilities and applications, for example, supply and reference diagnostics. This concludes my talk, and I thank you very much for your time and attention.